Good morning, my YouTube viewers. It's Crystal here. I'm just here because I want to do another code review with you. And the thing about doing the code review is it's a statistic code review. So before I actually go over the code, I want to go over a few concepts about the code before we go over it. And we're going to be going over the code in R and Python. So I was given the code in R and then I translated it in Python, which was a little bit complicated. I mean, obviously I've never taken a formal statistics course, and because I've never taken a formal statistics course, I'm learning all this on my own, which is why I'm having to give code reviews. So what we're going to be talking about today is the hypergeometric distribution, and so we'll just talk about what it is. In hypergeometric distribution in statistics, distribution function in which selections are made from two groups without replacing members of the groups. The hypergeometric distribution differs from the binomial distribution in the lack of replacements. Thus, it often is employed in random sampling for statistical quality control. A simple everyday example would be the random selection of members for a team from a population of boys and girls. So basically, that's how you can read the rest of this article if you want. Well, I'll just read this next paragraph. In symbols, well, it just talks about the formula, so you can read the rest of the article if you want. I got it from Britannica. Now, in the statistics, we have something called PMF and CDF. So we're going to talk about PMF, which is probability mass function. And then so in probability and statistics, a probability mass function is a function that gives the probability that a discrete random variable is equal to some value. Sometimes it is also known as the discrete density function. The probability mass function is often the primary means of defining a discrete probability distribution, and such functions exist for either scalar or multivariate random variables whose domain is discrete. A probability mass function differs from a probability density function in that the latter is associated with continuous rather than discrete random variables. A probability density function must be integrated over an interval to yield a probability. The value of the random variable having the largest probability mass is called the mode. So that's one thing that we're going to be talking about when we do the formulas. And the next thing we're going to be talking about is cumulative distribution function. It says in probability and in theory and statistics, the cumulative distribution function is a real valued random variable x, or just distribution function of x evaluated at x is the probability that x will take a value less than or equal to x. Every probability distribution supported on the real numbers, discrete or mixed as well as continuous, is uniquely identified by an upwards continuous monotonic increasing cumulative distribution function, satisfying lim fx equals 0 and lim fx equals 1. In the case of the scalar continuous distribution, it gives the area under the probability density function from minus infinity to x. The cumulative distribution function are also used to specify distribution of multivariate random variables. So that's your cumulative distribution function. So now what we're going to do is we're going to go over the code. We've got some examples, and then we will go over the code in the examples that we have been given. So what I'm going to do is I'm going to go ahead and run this program. And so we've got 3 examples, and then we'll go over the examples. And this is originally done in R, which I have translated to Python. So you will have the formulas, you will have the the code in both R and Python. And I got the questions from this YouTube video here. So I'll quote my sources. And it's the statistics and probability full course. That's where I've got the code. So we'll go ahead and just talk about the code. It says, let X be the number of spades drawn out of 4 draws from a deck of cards without replacement. If the deck is fair, then it is clear that X equal X tiddly square, tiddly, hyper brackets M equals 13, N equals 29, K equals 4. So what is the probability of getting a spade? So you're going to use D hyper brackets 1 because it's 1 spade. M equals 13 because there's 13 cards in a deck. N equals 39 because that's 52 minus 13 because there are 13 spades in the decks, but there's 52 cards in a deck. So M is 13 because you can choose from 13 spades, and N is 39. N is the other is 52 minus 13 is 39. So you've got 39 to choose from that aren't spades. And K equals 4 because you get 4 draws. And the answer to that is 0.4388475. The next question is, what is the probability of getting at most 3 spades? And that's P hyper, and that's brackets 3 because you want at most 3 spades, and 13 because there's 13 cards, 13 spades in the deck, 39 because 52 minus 13 is 39, and then 4 because you're going to have 4 draws. And the answer of that is 0.9973589. So you get a probability of 0.99. So that is your first example. So the next example is, I wonder if Stat 200 attracts more third-year students at a greater rate than other courses. Let X be the number of third years in the Stat 200 course. Of the third year students, M equals 356. The non-third year students, N equals 978. There are K equals 41 students, of whom 18 are third years. Does this support my claim? So the answer to that is 1 minus P hyper 17 is 18 minus 1. M equals 356. That's your third year students. N equals 9. No. N equals 978. That's non-third year students. And K equals 41. There are 41 third year students. And the answer to that is 0.01173,415. So we have the last example is, I wonder if Math 121 attracts fourth year students at a lower rate than other courses. Let X be the number of fourth years in Math 121 course. We know the number of fourth year students at Knox is M equals 278, and non-fourth year is N equals 1056. There are K equals 30 students in the Math 121 course, of whom X equals 3 are fourth years. Does this support my claim? So the answer to that is hyper, and then it's brackets 3 is the number of 3 fourth-year students in the class. 278 is the number of fourth-year students. 1056 is the number of non-fourth-year students. And 30 are the number of students in the class. And the answer to that is 0.09942,947. So that's the answer. So what I've done is I've taken this code and I have translated it into Python. So you will have the code in both R and Python. So let X be the number of spades drawn out of 4 draws from a deck of cards without replacement. If the deck is fair, then it is clear that X is Tiddly. I'm not sure exactly what the Tiddly means. Hyper, M equals 13, N equals 29, K equals 4. And so what you have to do is from SciPy Stats, you have to import HyperGeom. What is the possibility of getting a spade? And then the answer to that is HyperGeom, and then M equals 52 because there's 52 cards in the deck. N equals 13 because there's 13 spades in the deck. N equals 4 because there's 4 draws. And then it says .pmf 1 equals, you want to get 1 spade. And the probability of that is 0.4388475. And that's exactly what you got in R. And then the next question is, what is the probability of getting at most 3 spades? So the answer to that is HyperGeom, M equals 52 because there's 52 cards in the deck. N equals 13 because there's 13 spades in the deck. N equals 4 because you get 4 tries. And then .cdf3 is 3 because you want at most 3 spades. And then the answer to that is 0.99735. So, and that's exactly what you got with R. The next question, I wonder if the Stat 200 attracts more third-year students at a greater rate than other courses. Let X be the number of third years in the Stat 200 course. Of the third-year students, M equals 356, and non-third-year students, N equals 978. There are K equals 41 students, of whom 18 are third years. And then, does this support my claim? And then the answer is 1 minus HyperGeom, and then it's brackets M, and then I said 978 plus 356, and that's the total students. N equals 356, and that's third year students. Another N equals 41, because there's 41 students in the class. And 18, and then .cdf, and then you say 17, because 17 is 1 less than 18. And then your answer is 0.0173414. And that's exactly what you got in R. The next question is, I wonder if Math 121 attracts fourth-year students at a lower rate than other courses. Let X be the number of fourth years in Math 121 course. We know the number of fourth-year students at Knox is M equals 278, and non-fourth-year students is N equals 1056. There are K equals 30 students in the Math 121 course, of whom X equals 3 are fourth years. Does this support my claim? And the answer to that is hypergeome. So M equals 278 plus 156. And N equals, and so that's the total number of students. And N equals 278 because that's the number of fourth year students. Then N equals 30 because that's the number of students in the class. .CDF, 3 are fourth year students. And so your answer is 0.099429466. And if you look at that, that's exactly what you had in R. So what I've done is I've translated the code into Python, so you've got the code into Python. I will say it's very complex. The more I study statistics, the more I know I don't know. But I did spend time yesterday translating the code, so you've got the code. So I'm going to go ahead and close this video because I've accomplished what I wanted to accomplish. I would like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. And thank you so much for watching my video. I look forward to making more code reviews for you in the future.